I'm going to find my notes on Brandon Robinson. He's the co-founder and chief executive officer of Horizon Aircraft. Horizon's got a prototype, the Cavorite X7. That thing looks amazing. It can take off vertically, and then it's got a really cool transition wing system, unlike anything I've seen before. And I'm super excited to learn more about it so that it can convert to more of a conventional aircraft. So really, they're shooting for the best of both worlds, and it looks like they're getting it. It gives it more range, more cargo, more people, et cetera, than some of the conventionally designed aircraft. That's the plan. Brandon and his team have successfully raised over $25 million. They're actually a publicly traded company already. They've won numerous grants from a defense R&D competition. They're flight testing today, their large-scale prototype. And then in terms of Brandon's background, prior to launching Horizon, he actually flew CF-18s within the Royal Canadian Air Force for nearly 20 years. He graduated from the Canadian Top Gun Training School, and in the final years of his career, he was working on capital projects up to $4 billion, including acquisition of the F-35, and worked on a strategic plan to extend the life of their CF-18 aircraft. Brandon earned a Bachelor of Mechanical Engineering from the Royal Military College, as well as an MBA from the Royal Roads University. He's co-authored several successful aerospace patents, and he is an ATP. He holds an airline transport pilot's license. So with that, I'm very excited to hand the floor over to you. Take it away, Brandon.
Yeah, thanks, Andy. I really appreciate that. All that to say, I just know enough about some things to ask the really stupid questions to the team and kind of keep all the cats meowing in the same direction. So I, was trained as a mechanical engineer, of course, and then just went and flew jets for 20 years. So again, I have enough knowledge to just ask the really silly questions to the engineers and push the boundaries. So really appreciate the opportunity. Love this group, love this forum. I'm going to put up a presentation in a little bit. And before I do, I'm going to ask a couple of things. One, interrupt me lots, right? So this is a presentation that's been built for some investor folks. I'm limited to what I can present, but there's going to be a lot of interesting technical questions, I think, from this group. And so I would like to be interrupted, and I will give you lots of opportunity to ask me about things like how does it control yaw and in hover, and specifics about the aerodynamics in hover that I can talk about, how you're going to keep the whole thing cool, and all of those interesting technical bits that I think that this crowd might appreciate just a little bit more. So this is going to be less about business, more about cool technical stuff. But happy to really sort of dive down different rabbit holes on the way. So without further ado, let me present my screen. You should see, oops. There you go.
Got it.
Got it. Okay.
That's actually your view, not ours.
Right, we're in presentation mode still, but Brandon was able to pop it into full screen a minute ago. But it only, just so you know, we have it set up, Brandon, so it only works before the meeting. During the meeting,
yeah, exactly.
It never works.
Anyway, let's try this. Okay. So I will try making this into full presentation mode again. It all worked beforehand.
It sure did work perfectly before.
How's that?
No.
Not yet. We can see that
PowerPoint knows what you want to do, and they make sure that it doesn't happen.
Oh, no, that is fascinating. Okay. Well,
Air Force. For everyone watching, Brandon did test it before, and of course it worked absolutely perfectly first time out of the gate before the meeting.
How about contingencies in the Air Force? Let me try contingency mode. Let's try this one. Okay. Do you see it?
There it is. Done.
All right.
Well done, sir.
The tertiary contingency plan was enacted. Okay, so if the early morning coffee starts to wear off and my sort of voice fades into the background, a couple of things you need to know at the beginning. All right. So Horizon Aircraft, why do you care about us, what we're doing, and why we're different? Number one, we're operators first, right? So we were approached by a group of investors and said, can you build an eVTOL for us? And we said, does it even make sense to do this in the first place? And we realized that there was a kind of a growing gap in the marketplace. And we thought there was room for a tough, fast machine that operated a little more traditionally, and God forbid it has actual fuel on board. We'll go over that. It's hybrid electric powered, and just enough batteries on it to enable its distributed electric propulsion system. And it needed to go, we spent a lot of time focusing on the specifications. How far does it need to go? How fast does it need to go? How much does it need to carry in order to enable a solid business plan? And if you enable a solid business plan and give a machine to operators that they can make money with, then it will be widely proliferated, it will be bought, network efficiencies will make the world a better place. Instead of an if you build it, they will come approach, we really, really, really are laser focused on sort of the operators. And so myself, an operational background, 20 years in the Air Force. My father has been flying and building and cursing at airplanes for the last 50 years, to be quite frank. He flew his first airplane when he was 14. I had my first flight when I was 6 months old. My grandfather was a World War II bomber pilot. We are very, very operationally focused, and we want to deliver a product that is razor focused on the end user, if that makes sense. Trying to make things better. Couple of cautionary statements and legal stuff for a publicly traded company. No kidding. There were 7 slides that the lawyers wanted in here, and I got it down to 2. So there's going to be a skill testing question at the end of this, but there's the 2 slides out of the way. We were founded in 2013, and we'll get to the good stuff in a bit. But I really do want to foot stomp that we're quite an operational focused group, right? We build stuff in the real world, we break it, we fix it, we make it better. And I think that our success has been directly derived from that. I'm not going to go on and on about the advanced air mobility world. What I will say is there's a lot of folks, I think, reality is kind of setting in 2025. A lot of these designs, which I'm very excited about, the Jobies and the Archers and the vertical aerospace in particular, they will serve a certain amount of folks, and I think they will do really great work in the shorter range regimes. What we're focused on is a more operationally robust machine that can go regionally from city to city, 300 to 500 kilometers plus reserves. And I think, when you can do that, you also build in naturally a bunch of operational robustness that we'll get into that I'm pretty excited that we're focused on. And so there's our machine. For folks that aren't initiated, we'll go over this in a bit, and there's some really cool technical stuff here. There are always trade-offs in every design, and I would love to be interrupted, and you could ask me all sorts of different questions about it. We wanted a design wherein 98% of the mission would be flown on traditional wing-borne flight. Helicopters, love them. They will be around for a long, long, long time. We're not replacing, all the helicopters in the world. But they're a design that is completely built around takeoff and landing and hovering, right? You want to build a telecommunications tower. You want to do heli logging. You want to extract someone from a mountain that is injured and you have to hover for a long time. A helicopter is your machine. And we have no qualms with that. And I think the helicopters are an amazing design. However, they want to fling themselves apart on a constant basis. They can't glide very well at all. And, for the 98% of the mission, if they're just going from point A to point B, they're extremely inefficient. L over D of what, 4 or 5. Some of the technical folks will correct me if I'm wrong on that. But it's just an extremely inefficient way to travel from point A to point B. Anyone that's been on a tour lately, and I went on a helicopter tour in Hawaii recently, it is not a comfortable machine in which to travel. It is just terrible. There was always a search and rescue squadron attached to the fighter wings when I was a young fighter pilot, and every chance I got, I would go and ride in these things that would rattle themselves to death on a daily basis. And they're great, love them. But there's room for a machine that can maybe operate in a little more efficient manner. And so our machine is similar to fixed wing costs, a little bit more on a per hourly basis, but based on a helicopter operating cost, you're saving not only 20 to 30% on a per hour basis, you're also going twice as fast during that unit time. And those two things combined from an economic perspective, and on a per mile basis, you're saving 60 to 70% over a traditional helicopter. And again, in a specific mission where you're just traveling from point A to point B, which there are quite a few of those missions. So pretty excited about our design. I'll talk more about it in a minute. And there it is, right? So we're coming in at about 2860 kilograms. You can see our useful load in around the 700 kilograms. Subtract fuel from that to get payload. And so I'm talking to a bunch of folks that know exactly what that means. And so there's some realistic trade-offs there, but you're getting to your destination quickly, carrying a lot of, again, interesting, useful load. And you can see some max ferry distances quite a ways out there, 1,100 kilometers, 2-3 hours of flight, as it's, quite a quick aircraft on routes traveling anywhere from, I'll put it in knots. So we have a 250 knot max. You'll cruise in the low 200 knots, right? So in a 400 kilometer an hour range, going from point A to point B. And that is a very accurate and, again, a somewhat pessimistic calculation, but it's realistic. So how does it work, right? So anyone that's done a little bit of research on us knows that we have a unique and patented wing system. There's a lot more under the hood that I'd love to talk to this group in particular about, especially some of the experts on board. But essentially, you got 5 fans in each wing and 2 fans in each canard. Those are electrically powered. Now, that electrical power comes from 2 sources: rectified generator power from a certain amount of kilowatts on board from a generation perspective, and then also from the battery array. Each one of those fan units is electrically, thermally, mechanically isolated, line replaceable units. In case they break, you can drop one out, put it back in. It's meant to be a tough machine that can be, repaired in a remote location. And again, foot stomp, it is hybrid electric, right? So you take off, you burn through X% of the battery. En route, in the first 10 to 15 minutes, it will be able to recharge itself. And so you start the landing phase with full battery power. And for the technically savvy folks on board, full battery power means about the 90% level, right? You can't fast charge a battery all the way to 100% or you'll blow it up, and we don't want to do that. But because we have a lot less battery power on board, we can make that chemistry much more robust, if that makes sense. Think 21700 cylindrical cells, very high C rate discharge type of chemistry. That means it can be charged quickly without any issues. And in any sort of issue, you take off and you fly to a remote location. Maybe you're taking emergency medical supplies or organs to, or a doctor to some sort of remote northern location. You land, and in the process of landing, you have to do an overshoot and go around because maybe a cow walks out into the field or something, and now you can recharge yourself prior to attempting another landing as long as you have fuel on board, which is, by the way, again, I think I said this in the preamble, about 30 times as energy dense as even the best batteries. Our fuel on board allows us to recharge the aircraft and attempt another landing at that remote location. It can also operate as a normal aircraft. So you can rip down the runway, rotate, the gear is stressed for it. It's the location is of the landing gear and of the aircraft is such that it can rip down the runway, do a normal rotation, take off, and fly away like a normal aircraft. I think that's going to be important from a ferry perspective. It can also land like a normal aircraft at a normal airstrip, should you so choose. In between the vertical and the normal conventional takeoff, you have a really interesting spot where you can do a lot of short takeoff and landings. We actually think that this is going to be quite a popular mode for the aircraft to operate in. You offload the electrical array significantly, and you can take off in hundreds of feet, not thousands of feet, which opens up a lot of regional opportunities for nodes in your connectivity matrix. It's a bit of a diatribe, but I mean, we have a really interesting software tool that I can show some folks under NDA later, where we can dial in the distance of flight, the amount of reserves required, the mission profile, everything in it, and it can connect regional nodes, if that makes sense. And you can get a feel for, or regional operators can get a feel for what they would be able to do from a demand aggregation perspective in order to build their cases. En route, that's what it looks like. So the wings close. This is, again, our patented design, where the wings close and it flies 98% of the mission just like a normal aircraft. The trade-off is that there's some significant mass in the wings. You know, a lot of aircraft carry fuel in the wings, which is very heavy. And a lot of the battery mass is actually in the leading edge of the wings as well, which from a flight dynamics perspective creates some challenges from a flight controls perspective. But from a structural perspective, the mass is not centered in the middle of the aircraft, if that makes sense. Reduces bending loads and is much. There are a lot of positive aspects to that particular configuration. What I did mention, and this is something I don't actually say to a lot of folks and highlight, a couple of things. So this is in vertical mode, obviously. You know, if you would do a traditional wing loading calculation, you would say, okay, weight of the aircraft, 6,300 pounds. You would do the pi r squared times, 14, and you come up with a traditional wing loading. It's really interesting insofar as there is, and this was by design, a lot of low pressure region created over the forward and aft leading edge around the ducts, and you get a lot of assistance, if that makes any sense. I can't get into the numbers, but the traditional wing, blade loading calculations don't work when you want to analyze its hover efficiency. Roughly, I could say divide it by 2. If you do the math and then just divide it by 2, you're going to get pretty close. It also produces a lot of lift with any forward speed. So in a matter of 10 to 15 seconds, the aircraft is producing a very significant amount of lift over the forward section of the wings. The fans also work to adhere the flow to the rear section of the wing, if that makes sense. And you're under kind of more traditional control sooner than you might think. This was theorized. This is, critical in the design, and it's been proven out on a half-scale prototype, and we're proving it on the full-scale aircraft design as well. So a lot of really interesting things that came together more than the sum of their parts, if that makes sense. We also hide the empennage design, if that makes sense. So you're not going to see a lot of pictures of our empennage design because it's really unique. But there are some control surfaces there that really do help the entire situation, including a very, very stable transition to forward flight. We don't have rotating, massively rotating multi-copter situations. We simply ramp down the fans and close the wings in a very traditional fashion. The tail helps out quite a bit with that without getting too much into it. And it is a parallel hybrid system. So the pusher prop, which has beta mode, is connected directly to the main shaft of the turbo machinery. And so there's a lot of benefits there. And I'll get into some more of that. I have lots of patents I can show folks. Some renderings, and actually a picture on the lower left of our half-scale prototype that has a 22-foot wingspan. It weighs close to 600 pounds. It's a beast of an airplane, and it has flown hundreds of times. Touch wood, it has not crashed yet, and it is quite a stable airplane, which is fantastic. We got a business mode in the left. We have, of course, it's going to be great for doing disaster relief technicians. You don't need to find the world's longest extension cord when you land, right? It can recharge itself as long as you have fuel. And of course, medevac, we're making sure the cabin volumes and all the details are sorted out for medevac. For example, Again, from an operational perspective, medevac, you have to consider the oxygen and the amount of oxygen they typically carry on board, the ingress and egress of the stretcher, which is not shown there, the ability for the the care folks to be able to operate the systems, etc. So we're speaking with professionals in order to do that as well. I'm not going to get into this either. Of course, if you can build a helicopter that's effectively twice as fast and operates at a cheaper per hour basis, it can do lots of really cool stuff. And that's borne out in the operational use cases. Now, I'm just a really honest guy when it comes to this stuff. You can make these numbers dance. It really does. Joby is talking about 2,500 operational hours per year. The typical helicopter operates in the 400 to 500 hour spectrum. If we operate at twice that, here's our cost per seat mile. Very, very reasonable. But if you want to have a real conversation about this, please hit me up. There are so many variables in here. We have a cost model that has about 1,000 Excel lines put together. It has everything from oil to TBO costs on the turbine, and it's put together by a professional CFO that has operated helicopters before in a public company, and he really knows the stuff. The frustrating part that I have is there's never an apples to apples conversation with any of these companies. Again, there's the Joby 2,500 hour use cases. So you're just suddenly going to multiply your operational cadence by 5 over any normal helicopter operation in an aircraft that can't fly in bad weather. It's very challenging to come up with some of this stuff. So please challenge me, hit me up if you want some real conversations about this sort of stuff. And I kind of hit on it, right? So this is a company that's putting together an aircraft that is meant for bad weather, for difficult operational realities. We want it to be one of the first VTOLs that is certified for flight into known icing, and it will be IFR certified. So not a lot of helicopters in the world can fly in clouds, and certainly I think only 1 or 2 are certified for flight into known icing. We look for certification up to moderate mixed, and we're working with some of the partners like Certification Center Canada, whose founder is on our board, at just a very robust sort of bad weather program, and getting it certified for use in these types of adverse conditions. I think if you can build an aircraft, again, transition to and from vertical flight will be done in VMC conditions, so under clouds, but potentially once you're transitioned, then it's a traditional aircraft, and it can fly in clouds and into known icing up to potentially mixed moderate icing, which would be absolutely fantastic. Once you have an aircraft like this that can fly in bad weather, now you avoid all of those tragic helicopter accidents where they're trying to scud run underneath the clouds and invariably hit power lines and or crash into the ground. Lots of incidents where that's the case. And I think that this aircraft could avoid that, which is, I think, is something that's really cool. Again, each one of these slides is probably a 2-hour conversation, if that makes sense. This is a slide that tells you kind of where we're going. The highlight is we've tested a half-scale prototype. It's done extremely well and validated some of our computational fluid dynamics. We're building full-scale aircraft parts right now, and we should have a full-scale aircraft demonstrator in the next 24 months to 30 months, which would be absolutely fantastic. There she is. I love the chain coming up from the bottom. It's great. And like I said, it's still all in one piece, which is a tribute to the team's success. You talk to anybody else that's still, putting together a medium-sized drone that weighs 500-600 pounds. They crashed at least 4 or 5 of them en route to success. But prototype 1 is still ticking along really well. A lot of success along the way. A few folks probably write about it. I'm not going to belabor this. We're talking to everybody right now. So we got on the radar with an AFWERX DoD grant that put us in touch with a lot of major defense prime contractors. obviously they're interested in a helicopter that can fly about twice as fast, and a team of practical operators that is putting together just a really tough machine, that's focused on the specifications and mission accomplishment over signaling other things, if that makes sense. You already know about me. I'm not going to get into the people too much, but we have some world-class talent that's come on board recently. Our CTO is from Lilium. It had 400 engineers under him at one point. A lot of interesting world-class folks have reached out, and we're bringing them on board carefully over the next little bit. More demand than we can handle. I think the last position was 250 applications for engineering, but in any case, I just like to finish with saying that, you know, we're pretty proud of what we're putting together. I also am proud of the team for staying humble, accepting a lot of feedback from industry experts such as yourselves. We've done a poor job going to some of these events, and again, I would footstop Mike that we're committed to coming to some more of your events. We've just been so busy recently that it has been not possible. We'd like to start sharing some of the interesting things we're learning with the community. And again, just sort of humbly appreciative of the support as we go forward. So thanks. That's a sort of a quick presentation. I'm sure there's tons of questions. That can be a bit of a steamroller when I get going. So love to answer all the hard questions I'm sure that all these super smart folks have.
Fantastic. Oh, that was absolutely excellent, Brandon. Wonderful technology, and you've obviously been very hard at work. This stuff isn't easy. Um, I'll while I'll look for people to raise their hand. I've got a quick one. I noticed you've got a forward swept wing. I haven't seen that in a while since the last one I remember was the Hansa jet in the 60s. Is that about managing your center of lift when you're in vertical flight?
Yeah, it's a great question. This was a really tough one in the conceptual design phase. We went back and forth, and it was a really tough call. Okay, in any engineering situation, there's always trade-offs, right? What are the benefits of a forward swept wing? There's some stall benefits, right? You get root stall first. It's very stable from a certain perspective. When it gets into that stall and transition regime, which we thought would be an additional layer of benefit during transition, which is nice. It gets the main spar out of the way of some of the aft rows in the cockpit, if that makes sense, or I should say in the cabin. So it moves the spar back a little bit, which frees up some headroom, quite frankly. So you don't have a giant spar rolling through the aft portion of the cabin. It also offloads the canards and hover to a very precise level where, we can lose a couple of them and still be totally fine with it. Okay, so those are some of the benefits. I'm not naming all of them. There's some other in-flight benefits. What are the downsides? And again, we're just that honest company that we're hopefully that comes across that way. With the dual box beam spar structure, you're going to come across torsional rigidity issues, right? We can't translate any of or it's difficult. We can. I got to be careful what I say here. The skin structure normally absorbs some of the torsional stresses through shear, mainly, right? We're not relying on that, and we cannot rely on that with the current configuration with the movable skin, and that it attaches in a certain way. Again, I gotta be careful what I say in terms of our technology. It's much more complex than it might be initially looked at here. But say that we cannot absorb any torsional stiffness through the skin, then we have to be very clever about how we do that with the dual box beam structure of the main spar on each wing and the additional mass that we have in the wing, if that makes sense. So there's also some clever aerodynamic hover things that happen with that forward swept wing, right? When a bird comes into land, you see it curves its wings forward a little bit. There's reasons why that makes sense. There's reasons structurally why it doesn't make sense. But overall, the net positives outweighed the net negatives in that design. So
That's great. Yeah.
yeah,
No, thank you, Brandon.
that's a great observation, and that's the best I can do from without getting into proprietary sort of discussion about
Nope.
it.
That makes sense. Mike, I'll ask you to unmute and ask your question, and then Matt, you're next.
Great. Just a, a quick one. So you said first of all, thanks so much for the presentation. This is awesome. Really great work. Really impressive. You said that you guys have done hundreds of flights with your half scale demonstrator. Have you guys and you emphasize the chain? Have you done untethered flights and transitions yet?
Yes, untethered flights and flights all the way up to transition speed. The one thing that we have not done is close the wings yet. But I will say at that transition speed, the fans are at a very low RPM, if that makes any sense. Again, we've got to be careful here. And it's about 2/3 of the way to transition speed. It is almost on windborne flights naturally, with that lower configuration that adheres the flow to the aft portion of the wing. So we've transitioned fully to normal aerodynamic controls. If I'm, lifting the skirt a little bit, if that makes sense. So that's the best answer I can do, Mike. Great question. We're all the way to transition speed. The one thing we have not done is fully close the wings yet. That will happen.
Yeah, I think you can claim transition even if the wings are open, but
we're trying to be just real honest with folks, and they have most people have a certain idea of what transition means. It means getting into your final configuration, if that makes any sense. And so it gets tricky to discuss the fact that we fully transition the aircraft, but we haven't actually closed the wings all of the way yet. And so some analysts are waiting for that particular flight test to happen. So that we're right at the very end of that. We just ran out of good weather in Canada, to be quite frank.
Hey, Matt, let's
Come
hear
down
your
to the
question.
Southwest.
Congratulations, that's great.
Yeah, it's pretty exciting. Like I said, and it's a culmination of a lot of different flight tests to get up to that point. Obviously, we took it very incrementally. We visited the wind tunnel on several occasions, and so it was kudos to the team for making that happen.
Quick question on the turbogen prop system. Since that's set up to recharge the batteries, I assume some kind of generator built into the turbine system. Are you able to completely decouple the two, i.e., can you just run the generator without spinning the prop and vice versa? Because that'll open up some different con ops for you.
Yeah, and this is a really excellent question, to be quite frank, and coming from somebody who must have thought deeply about normal operations. We had two options, right? A serial or a parallel system. Went with a parallel system, so anytime the turbogen is spinning, the prop is spinning, if that makes sense. And in terms of its electrical generation capability, a series hybrid might make a lot more sense in the future once technology gets just a little bit further, where we could again spin the turbogen and keep the main prop still. And we have just applied for yet another patent on a special version of that I can't really talk about.
Sure.
That has a very unique generator configuration. Call it a starter generator configuration that could enable some different things. But for now, parallel system, our technical demonstrator is going to be a parallel system, most likely, with, again, the main prop attached to the main shaft of the turbo machinery. So when it's spinning, the prop will be spinning. Now, full beta mode, right? So you have station keeping abilities.
And so in general, you're just going to steal some of the shaft power for the generator as needed.
That's exactly right.
Gotcha.
Yeah.
Okay.
Yeah.
Got it. Thanks.
That's correct. No one's asked me about yaw control during hover yet. This is usually a question that I get.
Stealing my question.
Okay, all right, perfect. that lines it up. So Ian, you're next, and then Nick, you're going to ask about yaw control and whatever else you want. Ian, take it away.
Absolutely outstanding presentation. Also, huge congrats on the flight test and transition into without, the wings closed, whatever. I think it's fantastic. I wanted to ask, as at Maglavero, we do a lot of CFD and design with all sorts of fidelity of, low fidelity, medium fidelity, high fidelity tools. And I definitely appreciate some of the interesting phenomenon that happen with ducted systems interacting with bodies, either in a wing or in a in a body like this. When you guys were designing your transition corridor, um, how much of your time of that design process was spent in, what level of fidelity of tools, and did you end up needing to do a lot of it in, wind tunnel testing, just because some of these phenomenon like separation could be highly dependent on, the quality of the simulation, and at the end of the day, you trust, the physical reality before you end up putting a several hundred-pound drone into the hands of the gods. What was that process like, validating that before, actually doing it in practice?
Yeah, so Ian, great question. We have some folks on board that have designed and built and flown their own clean sheet design aircraft, right? Our lead composite guy has designed and built and flown two of his own aircraft, unique aircraft designs. That requires a lot of savvy, right, to still be around. And so I guess the way I would answer it at the 30,000 foot level is, we believe the computational fluid dynamics to a certain degree, and we use tools very sharply where they might be the most useful. Once we get a reasonable CFD result, then we'll build and test a real version of that. And then the important thing is to feedback, to create a feedback loop where, okay, now we've got real world testing results. Maybe they're 7% off of the, of the predicted results. Why is that the case? We adjust our models. We use the appropriate level of even first person solvers or whatever, or just like broad brush, flow works and from SolidWorks or etc. But the important thing is use the right tool for the right thing. Only believe the results to a certain amount, and then get it into the real world and test it and make sure that it makes sense and it is performing as predicted, and then calibrate the computational models. And you're right, and just the whole time having awareness that at some higher Reynolds numbers, there's going to be some other things that pop up, right? There could be some flow separation that results in a rotational stall scenario, that could be precipitated at the leading edge of the duct, for example. We're quite aware of all of the macroscopic things that could happen at the larger Reynolds numbers at the full scale, at the full scale, and we're realistic about how much this will scale up to, to 12,000 or 15,000 pound machines, right? So this current, 6,300 pound machine, we're quite confident that we have enough CFD to and the testing protocol set up to feedback to calibrate it, that it will work. That was a long answer.
And
One quick
it's perfect. And
follow-up.
Brandon, we have 2 minutes left and two
Okay.
questions to go.
Never
And
mind.
Ian, if it's okay, let's jump into our lightning round and tie it off in a 2 minutes here. Nick, you had a quick question, and Brandon, quick answer if you could, and then Pat, over to you.
Yeah, a quick question on yaw, and then a quick observation that the S-92 and S-76 fleet in the North Sea get 1,500 to 2,000 hours a year. So it is possible to get those kinds of numbers, but your machine will be very much easier because of the parts count and the maintainability. And then my question was, can you describe yaw?
Okay, so great point. Yaw. And this patent just came through. So stacked from highest to lowest, okay? You take a cross-sectional diagram of the wing. You're standing looking at the wing, basically. On a fan, you have the fan unit that rotates. You have the stator. And then on the outer two fans, you have a rotational grid that is about an inch thick. Think of it as a gridded vane system that rotates. And as the air goes through it, this gridded vane kicks the vector slightly offset. Okay, and so now you have a horizontal vector that you can work with. As long as you can rotate that grid, you can steer that horizontal vector. It is extremely effective in yaw control, so much so that it has done some damage in testing because it's so powerful. So we made it a little too strong, with very minor drag implications. So we have we have yaw control with that. We have translational control with that, deck level translational control. And if you add a beta capable pusher prop, as long as it's into wind, you have station keeping abilities through all of those means.
Hey, we just have a few seconds left. Patrick, can you finish this off?
Sure. Hey, Brandon, what exact Air Force contracts do you have?
So we had a USAF AFWorks R&D contract to develop the half-scale prototype. And I'm not at liberty to say right now what we're working towards with the defense primes or the USAF.
Are you concerned that Elon Musk and Doge might come after your existing Air Force contract?
I'm not going to get into that right now, but there's let's just say there's a lot of interest in it. When the technology is proven out, again, it's a kind of a no-brainer. A helicopter that can go twice as fast with some caveats is interesting to a lot of folks.
Hey, we're at the end of our hour, and what a great hour that was, Brandon. Big applause from all of us. Thank you very much. This is a super exciting airframe. You're doing some great, amazing work, and we're going to be very excited to have you back anytime that you want to give us an update, because this is a thrilling airframe and a great project. I'm glad to hear you're making such strong headway. So thanks for all of us for being here.
Yeah, I just really appreciate the opportunity, Andy. Thank you very much. Thanks to everybody that listened through my diatribes and my overly long answers. There's a lot under the hood, right? So I could answer each one of these questions is an hour-long conversation. But feel free, anyone on this call, to reach out to me anytime. I'm very happy to have a conversation with all of these highly intelligent folks.
Outstanding. Keep up the great work and come back anytime, Brandon. Thank you. We're going to be in touch.
Yeah, love you guys. Thank you.